In the climax of Christopher Nolan's Interstellar, the main character falls into a massive black hole. He drops through pure darkness, gets battered by a storm of sparks, and suddenly lands in a five-dimensional space where he can talk to his past self. It makes for incredible cinema, but what would you actually see if you took that dive? While they are often imagined as aggressive vacuum cleaners roaming the universe, black holes actually follow the same laws of orbital mechanics as any other heavy object. These objects represent the final stage of a massive star's life. For billions of years, a star maintains a balance between gravity pulling inward and nuclear fusion pushing outward. When that nuclear fuel finally burns out, the core collapses under its own crushing weight. The Indian-American astrophysicist Subramanian Chandrasekhar calculated a strict mathematical threshold for this collapse. His work, the Chandrasekhar limit, dictates that a star's core must hold more than 1.4 times the mass of our Sun to overcome internal pressure and become a black hole. A star this massive collapses into a pinpoint of matter so dense it breaks our standard laws of physics. To understand how that looks, we have to take a trip straight down into one. Albert Einstein's general theory of relativity provides the map for this journey. Einstein showed that space is a flexible mesh fabric rather than a blank, empty void. This diagram shows how that fabric reacts to mass. A heavy object placed on this 3D grid causes the space-time fabric to sag. A black hole possesses so much mass that it stretches the mesh into a steep, bottomless funnel. This extreme curvature dictates the behavior of everything nearby. It pulls on physical objects, warps the flow of time, and even traps light. As we approach the edge, you will experience those distortions firsthand. Our simulated descent begins at the outermost reaches of the black hole's gravitational pull, where the environment seems calm, even as the physics begin to warp. We are now entering a zone of gravitational time dilation. According to Einstein, as gravitational force increases, time itself begins to slow down. Inside your spacecraft, your watch ticks normally, but to observers back on Earth, you appear to be moving in extreme slow motion. For every minute in this intense gravitational field, years pass for the rest of the universe. This journey is effectively a one-way trip into the future of the outside world. Closer in, we encounter the accretion disk. This is a ring of superheated gaseous matter and debris orbiting the black hole at millions of degrees. The gravity here is so strong that the friction alone generates intense heat and light. The Doppler beaming effect creates a visual mystery. The side spinning toward us appears brighter, as extreme speed concentrates light waves. Gravity then creates an impossible halo, folding light from the back of the disk and bending it over the top of the sphere. While often depicted as orange in film, this disk emits high-energy X-rays. If human eyes could see those wavelengths, the disk would likely appear closer to an intense blue. The black hole acts as a massive lens, distorting light so severely that it breaks our basic visual intuition. Crossing into the photon sphere, we reach a point where gravity captures photons and forces them into a circular orbit. In this zone, the light bouncing off your own back orbits the black hole and returns to your eyes. If you looked straight ahead, you would see the back of your own head. Beyond the photon sphere lies the event horizon. This is the boundary where the escape velocity to leave the black hole exceeds the speed of light. Crossing this line results in total destruction. The gravitational difference between your feet and your head becomes extreme, stretching you into a stream of particles in a matter of milliseconds. This boundary represents the edge of the knowable universe. Information is trapped here forever, leaving the interior to pure theoretical speculation. At the very center lies the Singularity, a point of infinite density. All the mass of the original star is crushed into a volume so small that our mathematical models of space-time cease to function. Because science cannot currently explain what happens at this point of infinite density, speculative fiction fills the gap with ideas like the five-dimensional tesseract seen in Interstellar. If we pull back from the abyss to a macro view of the universe, the role of these objects changes. Supermassive black holes serve as essential gravitational anchors at the center of most major galaxies. Our own Milky Way galaxy follows this pattern. Millions of stars and planetary systems stably orbit a central supermassive black hole named Sagittarius A star. Maintaining a stable orbit keeps us safe. These gravitational anchors provide the structural framework for the cosmos, marking the final boundary of what we can actually observe and measure.